In a previous lesson, we learned about operators. So we are now ready to continue learning about the postulates of quantum mechanics, which tell us how we can extract information about the system from its state function using operators. Postulate number 2 of quantum mechanics states that for every dynamical property of a system, there corresponds an operator which must be Hermitian. What do we mean by dynamical properties? These are properties associated with the motion of particles in the system. So things like position of the particles, their momenta, kinetic energy, potential energy, and others. Why do we insist that the operator for a property be Hermitian? The reason is postulate number 3, which states that if a property of a system is measured, the only possible outcomes are the eigenvalues of the corresponding operator. We need the operator to be Hermitian because eigenvalues of Hermitian operators can be mathematically proven to be real numbers. By insisting that the operators are Hermitian, we guarantee that values predicted by quantum mechanics are real numbers. Let's go deeper into postulate number 2. What exactly are the operators? The simplest ones are the position operators. Position operators are multiplicative operators. The rule for a position operator is that if applied on a function, the result is just the function multiplied by the coordinate. For example, for the location of particle 1 along the x-axis, this is the rule. The operator is x sub 1 hat. If we apply it to an arbitrary function f, the result is x sub 1 times f. Here, x sub 1 is the x-coordinate of particle number 1. How would you define the operator for the y-coordinate of particle 3? The operator is y sub 3 hat. When applied to function f, the result is y3 times f, where y3 is the y-coordinate of particle number 3. For linear momentum, the operator corresponding to the component of the momentum along an axis is applied using the following rule. First, take the partial derivative of the function with respect to the coordinate. Then multiply by h bar over I, where h bar is Planck's constant divided by 2 pi, and I is the imaginary number square root of -1. For example, the operator for the x-axis component of the momentum of particle 1 is defined this way. The symbol is p sub x sub 1 hat. P stands for linear momentum. X sub 1 means we are referring to the momentum along the x-axis for particle 1. If we apply this operator on an arbitrary function f, what we do is take the partial derivative of f with respect to the x-coordinate of particle 1. Then multiply the result by h bar over I. Whenever we deal with functions that depend on more than one independent variable, we have to use partial derivatives. The partial derivative with respect to one of the variables is just the derivative if you were to assume that all the other independent variables are held constant. Note that instead of the letter D, we use this symbol, which sort of looks like a D. It's called the partial symbol. How would you define the operator for the component of the linear momentum of particle number 2 along the z-axis? Here's how. The operator is p sub z sub 2 hat, and when this operator is applied on function f, we get the partial derivative of f with respect to the z-coordinate of particle 2 multiplied by h bar over I. For other properties, we construct the corresponding quantum mechanical operators by doing the following. First, express the property in terms of momentum components using what we know from classical mechanics. For example, the classical expression for the velocity component along the x-axis, v sub x, is 1 over m times p sub x, where m is the mass. Here, p sub x is the momentum component along the x-axis. Recall that mass times velocity is equal to momentum, so velocity is equal to momentum over mass, or 1 over mass times momentum. Step 2. To get the operator we want, we replace the momentum components in the classical expression with momentum operators and treat everything else as multiplicative operators. In our example here, we replace p sub x by p sub x hat. So the operator for the velocity component, v sub x hat, is equal to 1 over m times p sub x hat. This means that applying v sub x hat on arbitrary function f involves p sub x hat applied on function f, then multiplying the result by 1 over m. Recall that p sub x is h bar over I times the derivative with respect to x. So we can also say that v sub x operator applied on function f means taking the derivative of f with respect to x, then multiplying by h bar over I, then multiplying by 1 over m. Let's construct the kinetic energy operator for one particle confined to move in one dimension. Let's say that the particle stays in the x-axis. The classical expression for kinetic energy, which we represent here by the letter T, is 1/2 times mass times the square of the velocity, which we represent by v sub x. We need to express this in terms of momentum components. The velocity along the x-axis is equal to the momentum along the x-axis, p sub x, divided by the mass. It should be easy to show that the kinetic energy is p sub x squared over 2m. To construct the operator, we replace p sub x by p sub x hat. P sub x hat means take the derivative with respect to x, then multiply by h bar over I. We do it twice since the p sub x operator is squared. H bar times h bar is h bar squared. Imaginary number I times itself is -1. So collecting all the constants gives us negative h bar squared over 2m. The kinetic energy operator for one particle confined to move in the axis is negative h bar squared over 2m times the second derivative with respect to x. Note that we are not using partial derivatives here since we only have one independent variable, x. We just have one particle confined to move on one axis. In 3 dimensions, the classical expression for kinetic energy is 1 over 2m times the square of the magnitude of the linear momentum, p squared. P squared is equal to the sum of the squares of the components along the Cartesian axis, p sub x squared plus p sub y squared plus p sub z squared. We have already seen that in one dimension, the kinetic energy is 1 over 2m times p sub x squared, and the corresponding kinetic energy operator is negative h bar squared over 2m times the second derivative with respect to x. It shouldn't be too hard to show that in 3 dimensions, we just need to add the second derivatives with respect to y and z. The sum of the 3 second derivatives is often abbreviated as the square of a symbol that looks like an inverted delta. This is called the del squared or Laplacian symbol. What about 2 particles in 3 dimensions? The kinetic energy operator will just be the sum of the kinetic energy operator for each particle. This is the kinetic energy operator for particle 1, negative h bar squared over 2m1 plus del squared 1. And this is the kinetic energy operator for particle 2, negative h bar squared over 2m2 times del squared 2. The 2 particles may not have the same mass, so we specify m1 for mass 1 and m2 for mass 2. We also specify subscripts for del squared since each particle will have its own set of Cartesian coordinates. Del 1 squared is the sum of the second derivatives with respect to the coordinates of particle 1, which are x1, y1, and z1. Similarly, del squared 2 is the sum of the second derivatives with respect to the coordinates of particle 2. You should have already learned that kinetic energy is energy due to motion, and potential energy is energy due to position. Potential energy is typically represented by the letter V, and you may see an expression like this. This expression says that the potential energy depends only on the coordinates of particles. The letter Q in lowercase is a generic symbol we use for coordinates. In other words, we don't expect the classical expression for potential energy to involve any momentum components, so the potential energy operator will just be a multiplicative operator. If we apply the operator on a function, we just multiply the function by whatever the classical expression is for potential energy. For example, for a harmonic oscillator, the potential energy is 1/2 times kx squared, where k is a constant. What happens if we apply the potential energy V hat on function f? Simple. We get 1/2 times kx squared times f. The operator for total energy has a special name. It is called the Hamiltonian operator, and its symbol is h hat. Therefore, h hat is equal to t hat plus v hat. T hat is the kinetic energy operator, and V hat is the potential energy operator. Example. For a harmonic oscillator in one dimension, the potential energy is 1/2 times kx squared, where k is a constant. What happens if we apply the Hamiltonian to function f? H hat applied on f is the same as T hat plus V hat applied on f. The definition of operator addition means that we apply T hat and V hat on F separately, then add the results. For a particle in one dimension, T hat is negative h bar squared over 2m times the second derivative. Applying it on function f means taking the second derivative of f with respect to x, then multiplying the result by negative h bar squared over 2m. The potential energy operator is multiplicative. So here, applying V hat on F means multiplying F by the expression for V. V hat F is equal to 1/2 kx squared times F. How would we write the Hamiltonian operator for atoms and molecules? We just need to add up the kinetic energy operator for each particle and the potential energy operator for each pair of particles. We treat each nucleus and each electron as one particle. Let's look at the hydrogen molecule as an example. We will refer to the nuclei as nucleus A and nucleus B, and refer to the electrons as electron 1 and electron 2. Then, the Hamiltonian operator will just be equal to the kinetic energy operator for nucleus A, plus the kinetic energy operator for nucleus B, plus the kinetic energy operator for electron 1 and the kinetic energy operator for electron 2, plus the potential energy operator due to the attraction between nucleus A and electron 1, plus the potential energy operator due to the attraction between nucleus A and electron 2, plus the potential energy operator due to the attraction of nucleus B and electron 1, plus the potential energy operator due to the attraction between nucleus B and electron 2, plus the potential energy operator due to the repulsion between nucleus A and B, plus the potential energy operator due to the repulsion between electron 1 and electron 2. By now, you should know how to write the kinetic energy operators. For example, for nucleus A, it is negative h bar squared over 2 times the mass of nucleus A times the del squared operator for nucleus A. The interaction between charged particles is called electrostatic or Coulombic interaction. The potential energy operators due to Coulombic interaction between nucleus A and nucleus B is given by 1 over 4 pi epsilon naught times the product of their charges QA and QB divided by the distance between them, RAB. Epsilon naught is the permittivity of vacuum. The formula is similar for other pairs. There are, in fact, other terms for potential energy besides Coulombic interaction. We'll address them at a later time.